Hello, we are starting 12-1, which is a little mini unit on some probability. It does seem like a jump from our last unit, jumping to unit 12, but we always like to cover this right before the ACT because you will see probability on the ACT. Okay, so there's some vocab words that you need to know as well as some concept bubbles. So take as much time as you need to pause and write down what you think is important. But our first word is mutually exclusive. Things are mutually exclusive especially in probability, if both events cannot occur at the same time. Okay? So if we had a box that contained 100 different balls or marbles, 30 of those are purple, 10 are orange, we're going to select one of them at random, and what's the probability of the following? So if it's purple or orange, our keyword there is or. That means to add. So notice I wrote that little note over here. That's important to have down. So purple is 30 out of 100. Or means to add. And orange is 10 out of 100. So 30 plus 10 is 40 out of 100. We can reduce that to 4/10, which would then reduce to 2/5. You could also find the decimal of that by doing 2 divided by 5 in your calculator, which is 0.4. If you times that by 100, you get that it is 40% probability. So for your target today, I'm going to ask that you keep it in fraction form, but please know that all the other ones are correct as well. What if I wanted to know that what is the probability that it is not purple and not orange? So that's called a complement. So we already found the probability of purple or orange. What if we want it to not be that? We're going to do 1 minus our previous answer. If fractions are not your friend, you type that in the calculator. If fractions are your friend, you find a common denominator and subtract. So the complement, the event and its complement should always add together to get 1. Okay. What happens if something is non-mutually exclusive? So if mutually exclusive means that they cannot occur at the same time, what if something could occur at the same time? We have this formula here that we like to use to help us. We're going to find the probability of one of them. We're going to add the probability of the other. That's the same thing that we were already doing. Nothing different. But what we have to do is subtract the overlap, because the overlap is getting counted once and twice, but in probability, it should only be counted once. So we have to subtract the overlap. So the example given here, we have a student-made target, and it includes 2 overlapping squares. We're going to assume that a sticky ball thrown at a target is equally likely to land anywhere on the target. What is the probability that the ball lands inside one or both of the squares? So as long as it lands in there, we're good. We got to remember that area is length times width. So the area of the big rectangle here is 1200, because 20 times 60. Area of the yellow square is 100. Area of the blue square is 100. And area of the green square is 25, because it's 5 times 5. Need to know all those things. Okay, so we're going to do yellow plus blue minus the green, because the green is the overlap. So the probability of yellow is 100 out of 1,000. Probability of blue is 100 out of 1,000. probability of green is 25 out of 1,000. So 100 plus 100 is 200, minus 25 is 175 over 1,000. If you do not like simplifying fractions, that's okay. Use your calculator. I'm going to show you with Desmos real quick. So if you type in 175 divided by 1,000, whether you're on the graphing one or this scientific one, if you hit where it says your answers show up on this side, there's a little bar there that it's a box with a line and a box. That's the fraction. It will make it a fraction for you. I messed up. That should be 1,000. There we go. And so my fraction is 7 over 40. You are welcome to turn that into a decimal or a percentage. But let's keep on rolling for the last little piece here, independent and dependent. So remember, if you are an independent, that means that you are doing it on your own. What you do and what someone else does, it does not matter. What you do does not depend on what they do, right? So here's some examples. We have 10 cards in a box, 5 are black, 5 are red. We're going to select from the box one at a time. If a card is chosen at random, then replaced. The key word here is replaced. Another card is chosen. Does the color of the first card chosen affect the possibility of the second card? Well, no, because all cards are still possible the second time around. Okay, but what if I do not replace? Okay, so that means if it's replaced, it's independent. If it's not replaced, it is dependent because, think about it. So let's say I draw out one of those black cards. Well, now in my bag, I only have 4 black cards instead of 5 black cards left to draw. So that does not work. So to save some time, I'm not writing all that out. But it's because it takes away one of your chances. And our last example here, what does that look like? Let's say we spin a spinner 2 times. We're going to say that the blue is 1/3 of the board and the red is 2/3 of the board. Okay? Oh, it's orange. My bad. It kind of looks red to me. What is the probability of getting the same color both times? And you want to explain. All right, so we could have the possibility of orange and orange, right? That would be the same colors. Notice I put a little note over there in pink. The word and means to multiply both events. So orange was 2/3 times 2/3, which is 4/9. Okay. For blue and blue, it's 1/3 times 1/3, which is 1/9. So that's how you do dependent events. If something were not to be replaced, your number may change a little bit. Okay. Now, to answer the question, what is the probability of getting the same color both times? That's an or statement. So what's the probability of getting orange and orange or blue and blue? So I add those together for the final answer of 5/9.